Hi, Physics 2. Mr. Janowski here. This is part 5 of the Chapter 37 slides, and this will be the final part of the Chapter 37 slides. So we're kind of getting through this chapter, and it's just going to all of a sudden come to a complete cold stop. I will make another video to kind of sum up everything we've done for the year, but this video will be the last part of this chapter. So in the previous two videos, we learned about generators and we learned about transformers. And in this one, we're going to learn of other applications of magnetic or electromagnetic induction that we see all the time and that we use as part of our everyday lives. So let's get started with that. So, what is a generator? A generator, it's kind of the opposite of a motor. A generator is a device that converts mechanical energy into electrical energy. So we have this loop of wire inside a magnetic field, and we're going to use some kind of mechanical energy to turn this thing. And magnetic induction is going to induce an EMF. And we talked about how to make an AC generator. You can add commutators and capacitors in different places and turn an AC generator into a DC generator. But yeah, we talked about an AC generator and this very nice mathematical relationship. If you look at this GIF down here, between rotational motion and sine and cosine waves. So yeah, math, it is so unreasonably effective. We love it. So we did this 2 parts of the slides ago. In the last part of the slides, we talked about transformers. So what is a transformer? A transformer is a device for increasing or decreasing AC voltage. So it has to be AC voltage. A transformer won't do this for DC voltage because that doesn't vary with time. But yeah, basically by having a primary coil around one part of this iron core and a secondary coil around another part, when you pass a current through here, you create a magnetic field. So you've got changing magnetic flux that gets picked up over here, and this induces a current over here. And based on the number of coils, the relative number of coils you have in each one of these, the primary and the secondary, you can change the voltage. You can use this to increase the voltage so that you can transmit it over long distances without losing a lot of energy. And then you can decrease it when you need to send it into a house for the people to use safely, because you don't want hundreds of thousands of volts going into people's houses. And then different devices, once the voltage is coming into your house at 120 volts, you may have different devices that will actually step that way up. So televisions, especially the old televisions, had transformers that stepped it up way high, and microwaves do, and some high current devices do, and fluorescent lights, I know they do that too. They need to transform the voltage up very high. More typically, you're going to want to lower the voltage for like your phone charger or an ordinary kind of device. But yeah, that's what a transformer is. So what are some of the ways we discussed of changing the magnetic flux? So look at this formula right here in the middle. Phi sub b is equal to BA cosine theta. And basically the ways we discussed of changing it is you can change B, A, or theta. So if you close this switch, you're going to have a changing magnetic field. So that's one way to change the flux. If you physically move your loop into or out of a magnetic field, you're going to change the effective area. And if you're turning your loop, which is what a generator does in this magnetic field, you're going to change the magnetic flux. So those are 3 ways to do it. So yeah, we've discussed generators and transformers, and yeah, these are hugely important for powering our modern world. So yeah, at the power station you have a generator, so it's going to use, typically, I mean there are other ways to do it. There's photovoltaic, but typically the name of the game is get something to turn. So it could be a hydroelectric plant where you've got falling water that's turning a turbine to do it. Other things, stations that use fossil fuels, they're going to use the heat that's released from the chemical energy to create steam, and the steam is going to turn the turbine. Or, there are different ways to do it. But basically, in general, you want to make something turn. So you're creating mechanical energy, and that mechanical energy is going to be turned into electric energy by the generator. And then you're going to have a transformer here to step up the voltage so that you can send it over huge distances with very low energy losses. And then before you get it into the buildings and the houses that, where the people are going to use it, you're going to have a step down transformer that's going to take that very high voltage and lower it to a much safer level. So, yeah, electromagnetic induction is used in generators and in transformers, but we use them in lots of other places as well. So, for example, right now I'm talking to you on a dynamic microphone. There are basically two kinds of, well, there's more than that, but there's two main kinds of microphones. There are what are called condenser microphones, and condenser is old-fashioned electronic speak for capacitors. Believe it or not, those are basically just a capacitor, and I don't want to go into that because that's a different thing. But we did learn about capacitors earlier in the year. But the microphone I'm using right now is a dynamic microphone. So induction is used to make a dynamic microphone work. So we didn't get the sound because, this year went a little off track. But sound waves are alternating regions of compressed or rarefied air. So compression or rarefaction, we would say. So lots of different things can create those waves of compressed or rarefied air. It could be a speaker cone. If you're listening to music from a speaker, or even in your headphones, it's basically a little tiny speakerphone. Could be your vocal cords that are vibrating the air. Whether you're a vocal music major or not. Could be a vibrating string. Could be a drum head. Could be a cymbal. Could be lots of things. But something is going to vibrate the air. So how does a dynamic microphone work? So in a dynamic microphone, these incoming waves of compressed and rarefied air are going to shake a little diaphragm, a little sensitive thing, and this diaphragm is connected to a coil, and this coil is around a permanent magnet. So as the airwaves come in and shake this diaphragm, it's going to move the coil back and forth around the magnet, so you've got a changing magnetic flux. So if you have a changing magnetic flux, that's going to induce an EMF. It's going to induce a voltage. So we have turned the vibrating air into an electrical signal. And then you can amplify the signal and do all kinds of things with it. So think of it this way. Very similar to how a generator and a motor are complementary devices, because a generator turns mechanical energy into electrical energy, and then a motor takes that electrical energy and turns it back into mechanical energy. Microphones and speakers are also very complementary. They're doing kind of the same thing. So a microphone is taking, essentially mechanical energy, the kinetic energy of the air, and turning it into an electric signal. And then different things can happen between here and here. You can record it in different ways, or just amplify it directly if you've got a loudspeaker or something like that. But yeah, what a speaker does is it takes that electric signal and turns it back into a mechanical signal. Mechanical signal in this case being vibrations in the air. So yeah, we learned about speakers last chapter. So yeah, another set of things that are basically complementary devices. And to this point, if you took, say you had like a broken fan, something like that, if you knew what you were doing, you could break that fan apart, set up a multimeter to different parts of it and measure it. And if you physically grab, a fan is basically, it's a motor with, fins attached to it to move the air. So if you grab those fins and started spinning them, and you've got your multimeter hooked up the right way, you're going to induce, you're going to create electrical energy. So you can use a fan kind of backwards as a generator. It'll be a pretty poor one, not a very useful one, but it will work. And in the same way, in some cases at least, you can yell into a loudspeaker, and you're shaking the speaker cone, and it will work kind of exactly like a dynamic microphone, and you can measure the signal coming out the other way. So not the best way to record audio, but it would actually work. So yeah, microphones and speakers are both examples of what are called transducers. So this is a more general just type of machine device. So it's a device that turns one form of energy into another form of energy. So yeah, a microphone is turning the kinetic energy of the air into electrical energy. A speaker is doing the opposite. It's taking the electrical energy and an electrical signal and turning it into kinetic energy of the air. So it's turning, an electrical signal into a signal of vibrating airwaves. So yeah, these are both examples of transducers. So lots of things are transducers. If you have a light meter, that's going to turn light energy into an electrical signal. If you have an electric thermometer, that does the same thing. It turns heat energy into an electrical signal that it then measures. All the sensors on the pixels of your camera, those are also transducers. They're turning light energy into an electrical signal. So transducer is just, it's a broad category of devices. The one thing they share in common is they're turning one kind of energy into another kind. So another thing where you might see the magnetic induction, if you play the electric guitar. So if you have an acoustic electric is an acoustic guitar, and it's got a microphone in it. So I don't know if it would be a dynamic microphone or a condenser microphone. Different kinds may use different ones. But yeah, it's basically just a microphone. Electric guitars work a little bit differently. So the pickups on an electric guitar, it's not just a microphone, it's working very differently with electromagnetic induction. So if we look at the pickup, if you're used to looking at a guitar, you see those little circles. I mean, they're typically visible. Sometimes you can't see that they're there. But these little circles are the tops of magnets. So you got these little magnets under each of the different metal strings. So on an electric guitar, the strings have to be metal, or they at least have to have metal in them. They might be nylon wrapped with metal, but there needs to be metal there because you need something that's magnetic and capable of being magnetized. So what's happening is each of these permanent magnets right here is going to induce, it's going to magnetize these metal strings above each of the pickups like this. So around that, you have many turns of this coil of wire. So this is what's really going to make the pickup actually work. So the fact that this string, if you take these strings and they're not moving, they're not going to induce any kind of EMF or any kind of current, because if they're not moving, the magnetic field is not changing. If, however, you pluck a string, it's going to vibrate, and that vibration is going to cause a changing magnetic field that the coil of wire, so the red in these diagrams up here, and this big coil down here, that's going to pick up the changing magnetic field, and that turns it into an electrical signal. So this is another type of transducer. So that's how a regular pickup works. If you have a humbucker, I forget exactly the real principle of this, but you've got a pair of these regular ones, and one of them will all be wrapped one way, and the other one will be wrapped the other way. And you can maybe barely tell here that these are all souths and these are all norths. And basically, in a clever way, you get these guys to cancel out any electronic, like, kind of background noise. It's bucking the hum is what it's doing. That's why these are called humbuckers. So that you're only getting the signal from the vibrating strings, and it's not picking up the electric noise from all the 60 hertz devices we have in our house, and any other electronic noise like that. But yeah, so that's how the pickup on an electric guitar works. So, any of you hipsters out there, me included, I have a vinyl record player. The cartridge on a record player also works with magnetic induction. So, yeah, this is really cool. This is I don't know if it's a scanning electron microscope or a tunneling. I think it's a scanning electron microscope image, a super close up of what the grooves on a record look like, and what the stylus needle actually looks like itself. So the stylus is all part of a bigger thing called the cartridge. It's what the record manufacturers or the record player manufacturers call the whole thing. So basically, yeah, this stylus, we can kind of see what's going on here. It's connected to this long arm like this, and the whole arm is able to move. And then in a stereo cartridge, you're going to have two different magnets here, one going this way, so up and to the left, one going this way, up and to the right. And maybe you can see that a little bit clearer on this one. So this is, the 45-degree view. This is the end-on view. So as this stylus is vibrated back and forth, these permanent magnets are going to move, kind of up and down along these ways, and they're going to create changing magnetic fluxes in one set of coils and in the other set of coils. And this is how you can get stereo sound with one needle. So if the thing gets pushed, back and forth this way, that's going to send a signal to the right channel. If part of it's also going back and forth this way, that's going to send the signal to the left channel. So yeah, this is neat stuff that we figured out. I don't know when they first started making stereo records, but it was at least in the 1960s, maybe before then. So yeah, clever stuff. Also, magnetic storage devices. So hard disk drives, which they're not as cool as the solid state drives, but at the time of this recording, 2020, it's still much cheaper to get big storage in hard disk drive than it is in the solid state drives. The flash kind of memory. But yeah, all kinds of magnetic storage. So hard disk drives, magnetic tape, so cassette tapes, VCR tapes, things like that. The magnetic stripes on your credit cards and things like that, they're all going to use induction too. So if you look at the magnetic media, so let's just say that this is tape, you're going to have little areas in this. They're called domains. And before you do anything to it, they're just going to be randomly aligned like this. So some of them are up and to the left a little bit. Some of them are left, down to the right. So they're all just randomly aligned. But as you pass this tape under, so let's just stick with the idea of a cassette tape player. So as you pass this under the recording head, I forget the point of having this bias signal that's above the human hearing range. I forget what the purpose of that is, but it serves some purpose, I'm sure. But anyhow, as you pass the randomly aligned domains under the recording head with the signal you're having, see, unfortunately, this stupid little gray bar shows up. If you look at the arrows going back and forth on the tape, you're going to have some going, straight one way, some going straight the other way. So this is how you can create a signal. Then when you pass that under the playback head, so now the tape is still going left to right. So as this is passing under the playback head, there's a magnetic field recorded on the tape itself, and as it passes under this thing, it causes a changing magnetic field. So now we have induction occurring, and that changing field causes a little EMF and a little signal that this thing can pick up. So you're turning that measurement of the changing magnetic field into a signal that you can, send through your tape player and now listen to your cassette. Oh, I thought I had made a review one for this. Apparently I hadn't. So yeah, those are our different examples of devices that also work on electromagnetic induction. So hopefully you found that interesting.